Assalamualaikum warahmatullahi wabarakatuh. Hello everybody, my name is Nisa Gultom. Today, we will learn about a topic of chemistry, that is colligative properties of solutions. Before we start to discussing this topic, do you still remember what solution is? Yeah, the solution defined as homogeneous mixture of two or more substances. One component of solution is present as solvent and the other component is present as solute. As we know, during winter, the countries that have 4 seasons will experience many problems. One, for example, is snow falling and cover the road or trottoirs, so it can be dangerous pedestrian due to slippery. To overcome this problem, chemistry has a large role. To melt snow, table salt is sprinkled on the highway. This problem solving based on knowledge about solution properties. It called as colligative properties. Through these learning videos, you will be able to analyzing the phenomena about colligative properties of solution and presenting the information results about principal usability of solution colligative properties in daily life independently. The colligative properties of solution are the properties that depend upon the concentration of solute molecules or ions, but not upon the identity of the solute. The colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Several units commonly used to express the concentration of solution. For example, molarity, molality, and mole fraction. Molarity is a convenience unit for use in stoichiometric calculation, since it's defined in terms of the molar amounts of solute species. M is equals to mole solute divided by L solution. Because solution volumes vary with temperature, molar concentrations will likewise vary. When expressed as molarity, the concentration of a solution with identical numbers of solute and solvent species will be different at different temperature due to the concentration or expansion of the solution. More appropriate for calculations involving many colligative properties are mole-based concentration units whose values are not dependent on temperature. Two such units are mole fraction and molality. The mole fraction of a component is the ratio of its molar amount to the total number of moles of all solution components. By this definition, the sum of mole fractions for all solution components is equals to 1. Molality is a concentration unit defined as the ratio of the numbers of moles of solute to the mass of the solvent in kilograms. Let's first remind ourselves about what vapor pressure is. The vapor pressure is defined as the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phase, solid or liquid, at a given temperature in closed system. What happens to the system if we add a solute to the solvent in question? the simplest terms, since some of the solute molecules will take up space at the surface of the liquid, this will limit the number of solvent molecules at the surface. Since only solvent molecule located at the surface can escape, the sheer presence of the solute lowers the number of solvent molecules coming and going, and therefore lowers the equilibrium vapor pressure. The relation between vapor pressure of solution component and the concentration of this component is described by Raoult's law. The partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in the solution. Note that the pressure you obtain from this equation is the new equilibrium vapor pressure of system with the solid included. If you want to know how much change has taken place, you will need to look at the difference between the new P solvent and the original P pure solvent. Vapor pressure lowering is equal to vapor pressure of pure solvent multiplied by mole fraction of solute. Now that we have seen how addition of solute to a solvent can lower its vapor pressure, let's see if we can figure out how this relates to the boiling point of the same solvent. The normal boiling point of a liquid is defined as the temperature at which vapor pressure is equal to ambient atmospheric pressure. The vapor pressure of a solution is lower because the presence of non-volatile solutes. It stands to reason that the solution's boiling point will subsequently be increased. Vapor pressure increases with temperature, and so a solution will require a higher temperature than will pure solvent to achieve any given vapor pressure, including one equivalent to that of the surrounding atmosphere. The increase in boiling point observed when non-volatile solute is dissolved in a solvent is called as boiling point elevation and is directly proportional to the molar concentration of solute species, where Kb is the boiling point elevation constant. Let's start this discussion with defining the normal freezing point. The normal freezing point of a liquid is the temperature at which solid and liquid phase coexist in equilibrium. Let's see if we can figure out why the freezing point is lower when we add solute to the solution. We already know that in order to freeze a liquid, we have to lower the temperature. As the temperature lowers, the solution becomes more odor as it moves toward the solid phase. This is the effect that works against the second law of thermodynamics. In short, entropy likes to increase, not decrease in the natural scheme of things. So, if we have to lower the temperature to a certain point to freeze a pure solvent, when we add a solute, we add the entropy of the system, right? This means that the temperature will have to be even lower than before. The decrease in freezing point of a dilute solution compared to that of the pure solvent is called the freezing point depression and is directly proportional to the molar concentration of the solute, where Kf is called the freezing point depression constant. The osmotic pressure of a solution is The difference in pressure between the solution and the pure liquid solvent when the two are in equilibrium across a semi-permeable membrane, which allows the passage of solvent molecules but not of solid particles. If the two phases are at the same initial pressure, there is a net transfer of solvent across the membrane into the solution known as osmosis. The process stops and equilibrium is attained when pressure difference equals the osmotic pressure. The osmotic pressure of a dilute solution is related to its solute molarity and absolute temperature, where R is the universal gas constant. As noted previously, the colligative properties of solution depend only the number, not the identity of solute. Electrolyte solution contain a higher number of particles than the non-electrolyte because in the electrolyte solution, the solute will ionize. According to Van Hoff, the value of the colligative properties of electrolyte solution is higher than the value of the colligative properties of non-electrolyte solution with the same concentration. This value is called as the Van Hoff factor. Taking into account the Van Hoff factor, the formulation of the colligative properties for the electrolyte solution must be multiplied by I, where N is the number of ions and alpha is the degree of ionization. Let's practice some calculations using these equations.
I will run, I will climb, I will soar. I'm undefeated. Oh, jumping out of my skin, pull the cord. Yeah, I believe it. Oh, the past is everything we were. Don't make us who we are. So I'll dream until I make it real, and all I see is stars. It's not until you fall that you fly. When your dreams come alive, you're unstoppable. Take a shot, chase the sun, find the beautiful. We will glow in the dark, turning dust to gold, and we'll dream impossible. Chase, I will reach, I will fly until I'm breaking out my cage like a bird in the night. I know I'm changing into something big, better than before. And if it takes 1,000 lives, then it's worth fighting for. It's not until you fall that you fly. When your dreams come alive, you're unstoppable. Take a shot, chase the sun, find the beautiful. We will go in the dark, turning dust to gold, and we'll dream impossible.
The properties of a solution are different from those of either the pure solvent. Colligative properties of solution is the properties that depend upon the concentration of solid molecules or ions. Colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Okay, it's all about the colligative properties of solution explained. Thank you for watching and see you in the next learning videos.